Cartesian coordinate system, so we have the x and y axes. The axes can be rotated. Still 90 degrees to each other. And then you have a force like this. So you still have Fx and Fy. I had hoped to hand the exams back today, but I was busy all weekend doing other work and grading both this class and my other course. I finished their exams handbook, but I didn't do yours. But I did look through enough of your exams to know that some of you have some real struggles so far. So my concern is, some of you, if I hand back these exams, almost no matter what you do on the file, you're not going to pass this class, and I don't want that. I'm sure you don't want that. So I'm going to offer something to you guys I've never offered before in hundreds of courses that I've taught. I'm going to give you a makeup exam. If you're not happy, I'm telling you now, I was hoping to hand back the exam today, and then you can see. If you're not happy with the grade you get, I'm going to give you the same exam this Thursday. Okay? So go, not identical, but the same material. The only difference is I'll change some numbers. So you can't just memorize it, but the same exact problems, okay? Thursday. If you're not happy with how you did, start studying now. That's why I'm telling you now, so you can study today, this evening, and prepare. And if you're happy, when I hand the exam back, you're happy with the score, you don't have to show up Thursday, okay? Because I said before that okay, I have, if you guys all do well, I can give you all good grades. If you do lower, then I'm going to grade on a curve, whichever helps you better. But there has to be a certain understanding of the material. I'm not going to pass everyone if you have no idea what's going on. And so this is your chance to make up for that, all right? So take advantage. Now you have an understanding of what the exams are going to be like. You have plenty of time. I'll post a solution set so you can look at how you're supposed to do it. The exam is going to be the exact same problems. I'm just going to change some of the numbers, some of the distances or whatever. Okay? This is your chance. Don't blow it. Don't not do it. And then I'll have the exams. I'll definitely try by tomorrow so you have a better idea. But you probably already know. I'll post a solution set later today, and you'll know. Oh, okay.
Is it regular class time?
It's regular class time. Thursday. Is that okay?
You probably did well. You probably did. I might show up for a no show.
All right, so let's go back to the we have forces, rectangular components of the force. We have the force is at an angle. We can break it up into the two components. Normally, x and y axes are horizontal and vertical, but they can be rotated like this. So what this says is x and y axes are perpendicular to each other, so they're 90 degrees to each other. And normally they're in the horizontal and vertical directions, but they don't have to be. They can be rotated, but notice that they're still 90 degrees to each other. Now let's talk about unit vectors. This is 0, 1, 2, 1, 2. So we have here, this is I, it's a unit vector, and we have J. They're both, the length of them, if I and J vectors is 1, the magnitude is 1, but they give a direction. Remember, a vector has magnitude and direction, so this is going to give our other quantities a direction, as we'll see. So you can imagine the I vector written like this. J vector is written like this. So I is the coordinates is 1 and 0 on the x and y, and J is 0 and 1. And so the magnitude is 1, both of them are unit vectors. So I is directed, as you can tell, along the x-axis, the horizontal direction here, and J is aligned in the y-axis. Here's F, here's an angle theta. The x direction, the y direction. This is fx and fy. Fx is fx multiplied by I. Darken that. I'll explain this in a second. Fy equals fy times J. So this darker indicator on the left, these are vectors. This and this, those are vectors. The fx, the lighter one on the right, these are just magnitudes. And what gives this direction, so this is just a scalar. Those are scalars, but I and J are vectors. I'm going to just circled them, so they're what I mean. In other words, the vector f of x, the force in the x, is a vector, but it's not just a magnitude, right? It has a direction. So it's equal to the magnitude of that vector multiplied by this little I, this unit vector. So the little I, since it's 1, it doesn't change the magnitude, but it gives it a direction. It like completely defines which way it's going. And then the vector f of y is this magnitude fy, not a vector, multiplied by the little vector j, which has also the value of 1. When we do 3 dimensions, there'll be I, j, and k. K will also be a unit vector. So then we can say, this is the vector f of this. So this is the force. So force is a vector. It has direction. It has magnitude. It's this. This is just a scalar. This is the value in the x direction. So just a numerical value. It doesn't have a direction. And then the I tells it that it's placed along the x-axis. And then fy is the magnitude, and then the j is a unit vector in the other vector. So that together makes up this vector. Fx and Fy are the vector components of that. Typically, Fx and Fy are called the components. so you take this, multiply by cosine, and that's that. Here we've got some sort of large anchor, let's say into concrete, and it's being pulled on with a force, like this, 500 pips, wrapped around here. This is 70 degrees from the horizontal. You can see which direction it's going. We have this component. There's going to be an Fx, and there'll be an Fy. So the applied force is a force of 500,000 pounds. It's about the limit what we can apply in the structures lab downstairs. We have the biggest hydraulic actuator in one direction is 400 kips, 400,000, but the other direction is 600,000. So we can apply more than depending if it's compression or tension direction. We modified it, we're changing it, I think I explained to you when we went down there. But we could apply over 1 million pounds of force, but now we've modified it. We had a lever arm, so we used leverage before for testing a large full-scale ship panel structures. But now we're moving on to ridge columns. Okay, the angle of the force, so let's say alpha is 70 degrees. And we just want to determine the horizontal vertical components of the force. Remember, we have, this is x and y, and then this is the I direction and j direction, right? So I always falls along the x, j is always along the y. Later, we'll add k along the z direction, okay? And those are unit guys, I, j. So when they're multiplied by something, they don't change the value. They don't change the value. So fx, the magnitude, is minus f multiplied by cosine of alpha, so that's minus 500 times the cosine of 70 degrees. That will be minus 171 kips. And that's with x defined to the right and y up. And then Fy is plus F multiplied by sine theta alpha. So that's 500 multiplied by the sine of 70 degrees. That's 470 kips. Now the vector Fx, so these are scalars, okay? Now the vector Fx is minus 171 multiplied by I. So the magnitude is 171, and now the I gives it it became a vector rather than, just a simple multiplying by this unit vector. The unit vector has a specific direction that's defined or connected with it, right? Fy, and this is a vector too, is plus 470. So So let's put plus here, just to make it clear. Multiplied by j. These are our two vector components of the force. This and this, right? Those are the, now these are both vectors, right? They're not just magnitude, but they're both vectors, but in one's in the horizontal direction, one's in the vertical direction. And then we can say F, this is a vector, this is the total vector, is minus 171 times I plus 470 multiplied by 2. This is the force vector, not the components. See it? So this is a vector, this is a vector, this is a vector. This vector written like this completely defines this, right? Because this magnitude here, this from here to here, this is 171 in the direction to the left, plus the negative. This is 470 in the positive direction. And then when we add the I and J, it becomes this vector. This is F. Magnitudes for other things too. So tangent of theta is just this over this. So it's the magnitude Fy over Fx. These aren't vectors. So the angle is the arctangent of Fy over Fx. might indicate what's a vector by making it darker and thicker. This is a vector, these are just magnitudes. Is that clear? Hopefully. Okay, let's go back to our problem. Okay, I'm going to take a break. I'll be back in a minute. Say we have a force vector applied to the top of this bolt thing that's concrete, and it's defined as 300I plus 1200. This is 300 kips and 1200 kips in both directions. So Fx, the force in the x, is just by looking at this is 300. The force in the y is 1200. Right? Tangent of theta is the y over the x, that's 1200 over 300. G equals 4. So that's 76.0 degrees. And the magnitude of that is the square root of 300 squared plus 12. 1,237. now we're going to look at addition of forces, different forces by summing the x and y components. These are all vectors, so R equals A plus B plus C. R is the resultant. A, B, and C are three different vectors. A is AX I plus B, I'm sorry, plus AY times J. These are all vectors. B is BX I plus BY J. C is CX I plus CY times J. So these are vectors, these are just the AX, BX, CX, AY, BY, CY, those are scalars, and then the multiplication of I or J turns them into vector components, okay? R equals Rx I plus Ry. So this is the resultant, which is written again here. This is the vector, but it's got a component, the resultant vector. So the resultant, we're adding three, in this case, three vectors together, right? And we have Rx times I plus Ry times J, so that's that resultant at some angle, right? We have two components of the resultant, which is from has equal to summing the different A, B, and C vectors together, but those also are written in their components multiplied by their unit vectors. These are all the same unit vectors, ij, 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 and so on. So we have a sub xi plus a sub yj. This is vector A. Plus bxi plus byj, that's vector B. Cxi and cyj, that's C. So we're doing this in components, right? Since we have same I, and the same I, three locations, we can separate that as A sub x plus B sub x plus C sub x times the unit vector I, plus bracket A sub y plus B sub y plus C sub y times J. These are the three horizontal components. sub x is a sub x plus b sub x plus c sub x. And r sub y is a sub y plus b sub y plus c sub y. So we have the components of the resultant, right? We're going to show three vectors now, vectors A, B, and C. Kips. Kips and 70 kips. This is up 10 degrees. 20 kips. This is 50 degrees. This is from the horizontal line. This is down 30 degrees. And we're going to call this one, this vector A, vector B, and vector C. They're all located. So we have A sub x. A is 30, so it's 30 and it's at an angle of 50 degrees from the horizontal, so this is x and y. So AX is 30 times the cosine of 50 degrees. I have 99.6. All right, 19. Looking in the wrong place right now. 19.3. B sub x is 20 kips times the cosine of 10. And C sub x is 70 times the cosine of 30. Those are all in the same kip units. A sub y is 30 times the sine of 50 degrees. $23.0. B sub y is 20 times the sine of 10. $3.5, which makes sense. It's almost it's only 10 degrees up, so there's a small vertical component of that. And C sub y is minus, because it's down, the down component, so it's minus 70. That's the magnitude multiplied by sine of 30. Minus 35 degrees. So I have R sub x is A sub x plus B sub x plus C sub x. So I just add 19.3, 19.7, and 60.6. 99.6 kips. 99.6. R sub y is a sub y plus b sub y plus c sub y. So it's 23.0 plus 3.5 minus 35. That's minus 8.5. So R, the resultant of this, is simply like this: R sub xi plus R sub yj. We have R sub x, so it's 99.6i minus 8.5j. Tangent of theta is minus 8.5 over 99.6. Just using the magnitudes there. That's minus 0.0853. So theta is the arctangent of that. Is minus 4.88 degrees. So let's see the magnitude. And then in terms of the magnitude, we have it's 8.5 squared is the hypotenuse times 99.6 square root. So the resultant magnitude is 1. So this is what the resultant looks like. Magnitude's 100 kips, and it's written like this. This angle down is 4.8. So you can see visually you get 3 different vectors acting, and we sum the components, we found the angle, and then this is defined here as it's 99.6i, which aligns that component. This is the x component, minus 8.5j, that's the vertical. So if you look at the resultant, it looks like this. You've got this part, which is 99.6i, and then you've got this part here of the resultant, which is the same as that value, 8.5j, and it's in the downward direction. Is that clear? vector product of two vectors, magnitude is equal to A, B, sine theta. Where the angle is, the angle between the two vectors A and B is given magnitude of C. So you have here B and some vector A, and then perpendicular to that is C. It turns out you multiply two vectors together where magnitude represents the area if this is a three-dimensional sketch. So A and B are going to be in the same plane, and the C is 90 degrees to that. And you get this area. And then this is, let's say, 90 degrees to this plane. B and A don't have to be 90 degrees to each other, but C is, if that makes sense. So A and B lie in, well, any two vectors, you can make a plane between two vectors, and then C is always 90 degrees to that plane. So the C is a scalar. It's and it's the A and B are the scalar value, the magnitudes of vectors A and B. So you have vectors A and B and C. So A and B, C are vectors. But every vector has a magnitude and a direction. So here we're using the magnitudes of those vectors. Okay? So they're obviously related. magnitude of A multiplied by the magnitude of B and multiplied by the sine of the angle between A and B. So A, B, and C vectors are what's called a right-handed triad. So you can put your fingers like this, all your three fingers like this, and put, let's say, your thumb in the X direction, then which would be the, let's say, A, then there's the B, and then the C, such that. So based on the right-handed rule. And so you put, let's say, your thumb and your first finger, those are the A and B's, and then the C, middle finger there, ends up being 90 degrees to that plane of A and B. Okay, like X, Y, Z coordinate system. I say right-handed because it's also possible to have the left-handed one. So this thing has on. So it's like X, Y, Z. And it's like the A and B are the X and Y, and then the Z becomes the C. As it says, as the X, Y, Z axes and the IJK axis. It says viewing from the top of C, the rotation is clockwise from B to A. This gives the direction of C. So in other words, here we have our triad, A, B, and C. So now you have to imagine climbing up there, right? And looking down from C. And then B rotates clockwise to A, right? If it doesn't, that means C is in the opposite direction. So this is how C is, you can imagine C being defined, because C could be up or down. Now, this is shown with B in a clockwise rotation from here, from above this plane, in other words. You have a clockwise rotation from B to A. B to A is not necessarily 90 degrees. They can be any angle between these two vectors, okay? But the C is perpendicular to this plane that A and B fall in. If you switch A and B, then C will no longer be up. It'll still be perpendicular to this plane, but it'll be down, okay? And then when you stand down here to look, it's still clockwise between the angles B and A. So if you switch, as we'll see, we switch B and A, then we get a negative, which means, so C comes out negative, which means it's down instead of up. Any question?
I was just gonna say, is it fair to relate A to X, B to Y, and C to Z?
No, not yet. A and B can be any angle. I mean, it's in the XY plane, let's say, and C would be, let's say, but A and B could be in any, they don't have to be in XY. A and B could be in any angle anywhere in space. And you have two vectors anywhere like that. And once they're defined, though, you can imagine a plane between my arms, my A and B vectors. They can be different lengths too, right? But there's a plane, and then the C one will be perpendicular to that plane, whatever that. So the plane can be rotated in 3 dimensions. There's nothing that says A and B, nothing here that says it's in the X and Y, right? So you just have 3 directions, 3 principal directions. Well, you just have A and B, and then C is always 90 degrees to that plane. Oh. Okay, well, see everyone tomorrow, and I'll hand back exams tomorrow. That'll be my goal. Like I said, I'm going to give you a makeup exam this Thursday. Start studying now. You know, if you're happy with what I give you back tomorrow, you don't have to take it. That's fine. Just going to show up that day.